All right, and I went ahead and started the recording here. So last class we were talking about, quantum numbers, and this is actually one of the toughest topics in Gen Chem 1 for a lot of students. But any questions on quantum numbers or anything else that we did last class? All right, so make sure you know your quantum numbers. I will guarantee you that you're going to see some quantum numbers on the next exam. All right, so moving forward, we're going to talk about periodic properties. So these are properties that repeat across the periodic table. Sorry, sometimes they, sorry about that. Sometimes they repeat from left to right, and sometimes they repeat going down the columns. So the first one we're going to talk about is elements of the same group or family have similar electron configurations and similar reactivities. So we talked about this aspect here before, the similar reactivities. But the reason that they do have similar reactivities is because of their electron configuration. And right here we're looking at the alkaline earth metals, and let's take a moment to look at them on the periodic table. So here's our periodic table, and this group 2A right here, these are our alkaline earth metals. And what we know is that all of them will end with S2. So if you were looking at beryllium, that would be a 2S2, magnesium, a 3S2, calcium, it's going to be a 4S2, and so on down. So all of the alkaline earth metals have that configuration that ends in an S2. They also all have 2 valence electrons. And it is because of this that they have 2 valence electrons in the S block, in the S orbital, that they all have similar reactivity. So our electron configuration actually tells us about their reactivity, and it predicts that similar reactivity in a group or family. And those groups or families, again, those are our columns going down the periodic table. And once upon a time I mentioned the further down you go, the more reactive they are. And that is because as you get further down, let's say radium right here has its outer electrons in the 7s. That is quite a bit further from the nucleus than, say, beryllium that has its outer electrons in the 2s. So whenever electrons are further from the nucleus, they're not feeling as much pull from the nucleus, and it's easier for something to come in and steal those electrons. And we'll be talking more about that today. But here is our electron configuration using the noble gas core. So beryllium again has a 2s, magnesium a 3s, calcium a 4s, strontium a 5s, and so on down the alkaline earth metals. All of them do form the 2+ ion so that they can take on the noble gas configuration. All right, so questions about anything here so far, talking about similar reactivity based on the electron configuration? All right, so next up we're going to talk briefly about atomic size. So a typical atom has a radius of about 1 angstrom, and we've seen angstroms once upon a time, and I told you that I would give you the conversion between angstroms and meters. So an angstrom is essentially 1 unit smaller than a nanometer. So a nanometer is 10 to the -9, whereas an angstrom is 10 to the -10. In other words, we could say an angstrom is 0.1 nanometers or 100 picometers. When we're talking about atomic size, we are often talking in terms of picometers or angstroms. So our atoms are extremely small, which you probably already knew. And we can measure the radius by measuring the distance between 2 nuclei and dividing by 2. So once upon a time, when we had just started this chapter 7 and 8, I talked to you about how we can use X-rays to actually find out where our atoms are. So X-ray crystallography, we're going to shoot X-rays at these atoms, and what's going to happen is those electrons are going to radiate out in kind of circles here. Sorry, my circles aren't perfect. And what we're looking at is what we call the diffraction pattern. So we look at where they cross over, and then we have our computer estimate where the nuclei must have been. So essentially we are back calculating where the nuclei must have been based on that diffraction pattern. All right, but what we do in order to figure out the radius, and let me We'll have this right here. So this right here would be our radius. So radius is halfway across the atom. Is we would shoot that X-ray, we would have the computer back calculate for us, and then we would find out, hey, how far apart, get a better color here, how far apart are these two nuclei? And these two nuclei need to be of the same atom, so 2 hydrogens, 2 chlorines, or so on. So we figure out how far apart the nuclei are, and then we cut that distance in half, and that way we can say, hey, the radius of one is half the distance that we would see if we were to measure the distance between the two nuclei. So any questions on that right there about how we actually determine the radius of an atom? I know it'd be so much easier if they were kind of life size and we can pull out our measuring tape and just measure across, but for things that are really small, it's much harder to figure out just how big they are. All right, so here's an example of that. Here is Cl2, so each of these are now a chlorine atom, and what we know is the distance between the two nuclei is 1.99 angstroms. So that means the distance between here and here, 1.99 angstroms. So if we want the radius of 1 Cl, we're going to take that 1.99 angstroms, divide it by 2, it looks like 1.99 divided by 2 into 3 sig figs. I'm going to call that 0.995 angstroms, like so. All right, so then what we're saying is the radius of one chlorine is slightly less than 1 angstrom, 0.995. So any questions on this one? Okay. And by the way, the 2 right here is a counting number. It's a total of 2 atoms here, so this is an exact number. Good question. So I hear a question about how we would convert it into picometers. So let's actually take a look at that. So here we have the conversion. 1 angstrom equals 100 picometers. So if we did want to convert this into picometers, we would have 0.995 angstroms. And for every 1 angstroms, there's 100 picometers. So it looks like we would have 995 picometers. Because picometers is actually a smaller unit than the angstroms. Picometers 10 to the negative 12. So any questions on that one, on that conversion between the angstroms and the picometers? Juan, did you maybe mean the nanometers? Yes, no? Okay. If you did mean that, or if you wanted to talk more about it, just let's see. No, I meant picometers. Just got, okay, no problem. But yes, this is how we would convert it if we wanted it in picometers. But a very good question. All right, other questions so far? All right. There we go. All right, once we have that approximate radii, then we can construct what we think the bond length would be. So here we have carbon, and it has an atomic radius of 0.77 angstroms. So we want to know what the approximate bond length would be in carbon tetrachloride. Now I know most of you haven't had a chance to watch that Lewis structure video yet, so I'm going to go ahead and do our Lewis structure for us. So here we have carbon with 4 chlorines, and we would put the carbon in the middle, and it would surround it by chlorines. Then we would count up our valence electrons, and we would find that carbon has 4 valence electrons and chlorine has 7 valence electrons. So we would do our count, and we'd say carbon, chlorine times 4, because we got 4 chlorines. And we said carbon has 4 valence, chlorine has 7, and we have 4 of those. So we add all this together, and I think, if my arithmetic is correct, 7 times 4 is 28, and then with 4 from the chlorine gives us 32. And I know this is kind of a crash course in Lewis structure, so do please make sure you watch that video. So we have 32 valence electrons to go around. I'm going to place chemical bonds, 2, 4, 6, 8 electrons used, because every bond is worth 2 electrons. Now I'm going to go to the outside. We've just used 8, and now I'm going to say 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. All right, so this is the Lewis structure for carbon tetrachloride. 1 carbon in the middle, 4 chlorines to the outside. We add up all our valence electrons, and then we bond everything together, then we satisfy all the outer atoms. And for those of you who have brief memories of Lewis structures from way, way back when, the 8 electron rule says every atom must have 8 electrons, and it does. So this is a satisfied structure. So again, if you're looking at this and being like, oh my god, that was way too fast, please watch that video. All right, but what this is talking about is the bond length in carbon tetrachloride. We have 4 identical bonds, so it really doesn't matter which one we look at. So I'm going to go ahead and choose this one here on the right. So what we're looking at is how far apart, I'm going to call this my carbon is, from the chlorine. And here what we're actually assuming is they're pretty darn close to each other, like so. And by doing that, we can say that the radius of the carbon plus the radius of the chlorine will give us the bond length. If you've ever seen a space-filling model, you see that the atoms are actually really close to each other. Even though we draw our Lewis structures, like we've got these great long bonds, those bonds in real life are not very long at all. And that's why we can do this as an approximation, but it is an approximation because they don't really sit right on top of each other. Like I've kind of drawn here that they are just about on top of each other, and that's what our estimation comes from, that hey, if you know the radius of each one, then you know the bond length. It's not entirely true because they do have a little bond in between them, but it's a small bond. And that's why we can make this approximation that if we know the radius of each one, it's about the same as the bond length. All right, so that said, let's go ahead and get those radii. So the radius of carbon, we're told is 0.77 angstrom. And then the radius of the chlorine we just solved for, and we call that 0.995 angstroms. Like so. All right, and again, this is just an approximation because what it doesn't do is cover the actual distance in between the atoms. All right, so here we're going to say the bond length, oops. And this is between carbon and chlorine. It's going to be 0.77 angstroms plus 0.995 angstroms. So I'm going to take that 0.995, add in the 0.77, and I'm going to call this 1.77 angstroms like so. Oops. Notice because we're doing addition and subtraction, we're using our addition-subtraction rule. And what that means is that we're counting digits after the decimal. So 2 digits after the decimal, 3 digits after the decimal, we go with the smallest number, which is 2 digits after the decimal. All right, questions on anything I did here to get that bond length between the carbon and the chlorine? Good question. So do the atoms maintain an even circle, or do they tend to become more ellipses? I would say they definitely do not maintain an even circle. And depending on what they are, like they're a d element and their outer orbitals are going to be d's, they could be ellipses, but they could even be slightly different shapes. So we kind of conceptualize them as circles like this, but they absolutely don't have to be circles. One of the things we're going to talk about today is the shielding effect, and we're not going to get into kind of the nitty-gritty that you would if you were to become a chemistry major and take your senior level classes. But if you were to do that, it's called it's actually advanced inorganic chemistry, your senior level class. You're actually going to look at how some of the orbitals are not symmetrical and how that affects the core of the atom. So definitely we have atoms that are either ellipses or not even symmetrical at all because of those d orbitals and the f orbitals. Very good question. This circle that I'm drawing, that's just it's just the way we like to conceptualize them, but they definitely do not have to look like a circle. All right, other questions? These are all great questions, so please feel free to type in or unmute and ask if you have any questions. All right, so next up are our trends in atomic size, and you'll find as we're going through these trends that I drew my arrows a little different than most textbooks do, and the reason is I think it's easier if you just memorize one set of arrows rather than saying, hey, for size it goes this way, for ionization it goes that way. If you just memorize one set of arrows, I think your life gets so much easier. So for all of the trends I'm about to show you, the arrows will go up and to the right. And we're going to take a look at the atom here in the upper right and one of the ones in the lower left. This picture just happens to cut off the bottom row. I'm not leaving out the sixth row on purpose. But here we're talking about our trends in atomic size. So helium is an extremely small element, and the closer you get to helium, the smaller your elements are going to be. And rubidium in the lower left-hand corner is a very large element, and the closer you get to rubidium, the larger it's going to be. So one way that students in the past have remembered this is RB could stand for, not roast beef, but real big. So if you think of real big in the lower left-hand corner, that will help you to remember that the lower left-hand corner are going to be your real big atoms. And then if you can remember the helium, it's bouncing around inside of a balloon. Maybe when you were a kid or when you take your kids to Disneyland, they've gotten the Disneyland balloon and they're walking around happy with their little balloon. That tiny little helium was bopping around inside of there. So helium is one of our smallest elements, while real big is one of our largest. So that can help you to remember the trend that we get smaller essentially the closer we get to the helium. So going up and to the right makes us smaller, going to the left and down will make it larger. So closer to real big, it's going to be bigger. Closer to helium, it's going to be smaller. And we're going to talk about why those trends occur, but any questions on anything there so far? All right, so first I want to talk about the size with respect to a group. So here you're going up and down a column, and what we know is that our s orbitals, they look a lot like those Russian dolls. In fact, all of our orbitals do. When you have the first energy level, it's the tiny one. The second one, it's got sort of a shell on top of it. So it's got a second doll that's kind of sitting to the outside. Then the third one has a third shell on top. And the fourth one has a fourth shell on top. So as you go down any group, your atom is going to get larger. And it's larger because it has more shells. So it's at a higher energy level, and each energy level adds one of those shells. So as you go up, it's going to get smaller because it has fewer shells. So one of the ways I remember this, and for those of you who hate my analogies, just feel free to close your ears for a moment, is I think about putting on jackets. So being a California person, Southern California person. When I was younger, sometimes I'd go visit someone in Northern California or in a cold place, which, you know, anything below 60 degrees is freezing for us. And I didn't have a big snow jacket, so I just put a whole bunch of jackets on. So here's me in my t-shirt. Oops. So this is me in my t-shirt, and then maybe I had a flannel, and then I put that on, and then maybe I had a sweatshirt on, and then maybe I had a jean jacket on top of that. So I was getting bigger and bigger and bigger as I put on each layer of jacket because I didn't have a big heavy jacket. Now I would get inside someplace and I was like, oh, it's warm in here. And now I had to take off first the jean jacket, then the sweatshirt, then the flannel, and then finally back to my original t-shirt. So if you can think of these as shells, as jackets you're putting on as you go down the periodic table, and jackets that you're now taking off as you go up the periodic table, that can help you to remember why it gets larger going down and smaller going up. But any questions here on this idea of we get larger going down because we have more shells, and we get smaller going up because we have fewer shells? So next up, we're going to talk about why atomic size decreases as we go from left to right across a row. And this is a true periodic property. So periodic meaning from the periodic table. And so here, as you go across a row, we say the effective nuclear charge, Z effective, increases. I'm going to show you how to calculate Z effective. But what Z effective is I think of it as the power of those protons, the power of the nucleus. How well can they bring those electrons towards themselves? So if you think of an atom, and the inside of the atom, here's your nucleus, and on the outside here, these are your electrons. Now, once upon a time I told you that there is a huge amount of empty space here in between the nucleus and the electrons. And I said it was sort of like a sports stadium, like a football stadium. And here you're placing a tiny little marble on the center of the field, and the electrons are outside of the stadium. That's how far apart they are. So there's got to be something that keeps those electrons from drifting away. And it is the charge of the nucleus, the positive charge from the protons inside the nucleus. So that nucleus is drawing these electrons in. And the size of the atom depends on how well those protons are drawing the electrons in. So here, we want to know how powerful is your nucleus. And the Z effective, the effective nuclear charge, this is the charge that's actually felt. Oops, let me get a different color here. It's actually felt by these electrons. So the electrons don't feel the entire power of the nucleus, and that's because we have something called the shielding effect. So there are some inner electrons that act as a shield. They kind of protect those electrons on the outside. And so the Z effective, again, is how much of the nucleus do those outer electrons actually feel. So let's go back over here. And what we see is the effective nuclear charge increases as we go from left to right. Essentially, the nucleus gets stronger as we move towards the right of the periodic table. So the outer electrons, they're more attracted to the increased nuclear charge, and therefore they're going to sit closer to the nucleus, and this is what makes for a smaller atom. So again, the more powerful your nucleus is, the more the electrons are going to sit closer, and the closer those electrons sit to the nucleus, the smaller your atom's going to be. So again, we're going to go through this in more detail. We're going to do some calculations, but any questions on anything here? All right, so before we do, I want to remind you that we have outer electrons. Those are called your valence electrons. They always sit in the highest energy level, which we've called N in the past when we did our quantum numbers. And then we have core electrons. And so these are electrons that are not in the highest energy level. So let's just take a look at what we mean by outer versus core electrons. So let's go ahead and take a look at sodium. So just for fun, if we were doing the electron configuration for sodium and we wanted to start with our noble gas core, our noble gas abbreviation, what would be that abbreviation for sodium? How would we start off this electron configuration using a noble gas? Excellent. So I'm seeing Ne, neon. Perfect. So up and all the way to the right. Does everyone agree that we would start here with neon? Excellent. All right. So we're starting with neon, and then what comes next? All right, so I'm seeing a 3s, and I'm going to go ahead and say 3s1. So what do you all think of this electron configuration for sodium? All right, excellent. So let's go ahead back, and we're going to say neon 3s1. So what I can say is this neon right here is holding our core electrons. These are the inner electrons. These are the electrons that should not be coming off of the atom. So the atoms only do chemistry with their outer electrons, never the core electrons. Now here we have our valence electrons. So when you use the noble gas core notation, that abbreviation, the noble gas shows you your core electrons. But we could have written it out. We could have said 1s2, 2s2, 2p6, and 3s1. If we were to write it out like that, then you would be looking at the highest energy level right here, which is 3. Those are your valence electrons. And here we have our core electrons. So again, the core electrons sit towards the inner, they are the inner electrons, so they're sitting closer to the nucleus, and the valence electrons are on the outside. So any questions on anything here? Let's see. So I'm seeing a question about so size based on the shells, not the nucleus only. So the nucleus for all of these atoms is extremely small. Oops. There we go. Nucleus is extremely small, so small that it doesn't, we say that it doesn't contribute to the size of the atom. However, the way the nucleus does contribute is through its power. If it's got more protons, if it's more powerful, it drags those electrons in. But in terms of what truly makes the size of the atom, it is the electrons, because the nuclei is so small, we say it essentially has little to no volume for all of the atoms. So essentially, if you're a tiny atom, your electrons are close. If you're a large atom, your electrons are far apart, and it's just those electrons that determine are you tiny or are you larger. But it is the nucleus that controls whether the electrons are small, or I should say not small, but whether they're sitting close to the nucleus or whether they're sitting further apart. Does that sort of answer the question? Okay, perfect. All right, so other questions here so far? Okay, so I want to use another analogy, and again, those of you who are like pure chemistry, no analogies, feel free to cover your ears for a moment. So what's going on here between the core electrons and the valence electrons? So if you want to think of the valence electron as the youngest daughter, son, child in the family, and that young one is always trying to get in trouble, and they've got a older sibling that really cares about them, maybe a little too much, and kind of enables their recklessness, and is like, hey, don't worry, little valence electron, I'll cover with you. I'll cover with you for mom and dad. I'll make sure that they don't know you're out of your bed and down the street doing whatever. So the core electron acts as a shield, and this core electron essentially keeps the protons busy doing other things, so the valence electron doesn't feel as much power. So that's why we want to separate these into core and valence electrons. So we care primarily about how much of the nucleus the valence electrons feel, because it is the valence electrons that are then controlling the size of the atom, while the core electrons are trying to be good big brothers and sisters and kind of cover with the parents. They're trying to shield the valence electrons, not let mom and dad know that the valence electrons are getting into trouble. Okay, so let's go ahead and take a look at this. So here, our calculation for Z effective, which is the effective nuclear charge, is going to be Z minus S. And first of all, I just want to mention that this is an approximation. It's a very rough approximation. Again, those of you who are like, I love chemistry, I'm going to make my whole life about chemistry now. If you did go on to become a chem major in that one of the last classes you take, that advanced inorganic chemistry, you would find out the true calculation, and you'd find out that D electrons, because they're not symmetrical, they don't shield as well. And you'd find the same thing for F electrons. They're not very good shields because they're not symmetrical. However, here we're just doing an approximation. So Z minus S where Z is the atomic number or the number of protons, and S is what we think of as the shielding factor, and for us that shield is going to be the number of core electrons. Again, if you go up into higher levels of chemistry, you'll learn that the shielding factor actually has a little bit more to the calculation, but for us it's going to be the number of protons minus the core electrons. All right, so let's take a look at some examples. All right, so here is magnesium, and in here we've got 12 protons. And then here in red, these are our core electrons, and they are acting as a shield. And they are shielding the outer electrons, which I've just colored in blue. They're shielding those blue electrons from the power of the nucleus. So here we had originally a plus 12. Those were our protons, and we've subtracted out 10 because here in magnesium we have 10 core electrons, and we end up with a Z effective of 2. So again, 12 are the number of protons. Move this a little bit. 10 is our core electrons, and 2 is our Z effective, the effective nuclear charge. So if you were a valence electron in magnesium, you would feel a charge of plus 2, not the original plus 12, because your big siblings are keeping some of those protons busy right now. So you only feel the plus 2. So any questions on anything here so far? I know this is kind of a weird concept to wrap your head around. Okay, so let's take a look at chlorine. And here in chlorine, there are 17 protons, and we see that right over here in our calculation. And now we have 10 core electrons. And we see that right over here. And here are our valence electrons. So what those valence electrons feel are a plus 7. And remember, the electrons are attracted to the protons because of their positive charge. So in chlorine, if they feel a plus 7, they're going to sit closer to the nucleus than if they feel the plus 2 in magnesium. So magnesium's valence electrons are going to drift further apart. They're going to drift further from the nuclei. But in chlorine, because it feels a plus 7, they're going to sit closer to that nucleus. So any questions about that idea that the greater the effective nuclear charge, the closer it's going to sit to that nucleus? So because of this, I'm going to say that our chlorine is going to be smaller. And again, it's due to that higher effective nuclear charge. And our magnesium, I'm going to say, is larger. It's due to the fact that it has a smaller effective nuclear charge. So another analogy that I have, thinking about those valence electrons as sort of wayward children who like to sneak out of the house at night, is if you have an effective nuclear charge of +2, think of it as the power of the parents, they're not as good at reining in their children. So they're +2, they're really busy, they just don't have enough time to keep an eye on those valence electrons, and those valence electrons just journey a little bit further out from home. And now in the chlorine, the power of the parents are a little stronger. They're a +7, and they make sure all of their little valence electrons are tucked into bed at 6 p.m. sharp because it's a school night. So the higher the effective nuclear charge, the more those protons are controlling those electrons, and the more those electrons are going to obey, and by obey I mean sitting close to that nucleus. And so that is what draws them in, makes that a smaller atom. Any questions on anything here? Okay, so let's keep going and let's talk about how to actually do some more calculations. So again, Z effective is Z minus S, where Z is the charge of the nucleus, and that is another way of saying the number of protons. And S is a screening constant, and this right here is an approximately equal sign. So it is approximately equal to the number of core electrons. So again, we're doing the sort of simple calculation with the core electrons. Those of you who are like, that's not good enough for me, I want to do the real calculation, that you would learn in your senior level chemistry. You would learn how to find the real screening constant, but it is close to the count of core electrons. All right, so we're going to calculate Z effective for these atoms right here. So I'm going to start off with the lithium. And I know that Z effective, and by the way, I have a tendency to cross my Z's, but I don't always do it, so I apologize if that gets confusing, but I cross them so they don't look like 2's. So that is the original count for the protons minus S, which will be our core electrons. So let's go ahead and start with that lithium and go to our periodic table. All right, so here is lithium right over here, and the first thing that we need to know is how many protons it has. So how many protons does it have? Excellent, so I'm seeing 3. Do you all agree? Excellent. So it has 3 protons because that 3 right up there. So remember, the number on top is the atomic number, but it is also the number of protons. So once upon a time, way back when, I did tell you that Z is an abbreviation for the atomic number. So I'm going to go ahead and say 3 protons here. All right, any questions about where that 3 came from? All right, so next up, let's take a look at what its electron configuration would be. So if I'm going to start with lithium and I'm going to do the noble gas abbreviation, what noble gas would we use here? All right, so I'm seeing helium. Excellent. So we have helium, and then we would have a 2s1. Any questions on how we got that helium 2s1? All right.
Yeah, helium.
Mm-hmm.
I was just curious on how we got the helium again.
Okay, no problem. So whenever we need that noble gas, we go up and we go all the way to the end, and so it's always the noble gas that immediately precedes the element.
Gotcha, thank you.
You're welcome. All right. All right, any other questions so far? And please don't be shy about jumping in. If you got questions, you can talk or you can type into the chat box. If you have the question, there's probably 10 other people who have the question and who are counting on you because they're too shy. Okay, so inside of helium, how many electrons are there? Excellent. Excellent. So I'm seeing 2. So this number is also the number of electrons as long as it's a neutral atom, and we are talking about neutral atoms here. So we're going to say that there are 2 electrons in helium. So here I can say that there's 2 core electrons, and 2s1 means that there is 1 valence electron. You could also tell your valence electrons by looking right up here. And another way to determine core versus valence electrons is that if you know lithium has a total of 3 electrons, and you were to look right up here and say, hey, I know it has 1 valence electron, you could then determine that it must have 2 core electrons. So several different ways to determine your core electrons, but any questions on how you would find those core electrons? So you can either use that noble gas abbreviation and look at how many electrons are in the noble gas core, or you can take your total electrons, which is going to be the same as the number of protons because these are all neutral elements, and then you're going to subtract out the valence. And remember, the valence is right up on the top with the exception of helium, who is playing hooky. It actually has 2 valence electrons and belongs on the other side of the periodic table. But any questions on determining core electrons? All right. So lithium, 3 protons minus 2 core electrons gives us a +1 charge for our effective nuclear charge. And by the way, this is the charge of the nucleus. The only things that you have inside that nucleus are protons and neutrons, so it must be a positive charge. So always a positive charge coming from that nucleus. So any questions on how we found lithium to be a +1 for its Z-effective nuclear charge? So just to draw this out, to take a look at what's going on, so this is our lithium. Here's my little nucleus. Here is my first energy level. Here's my second energy level. And what we're seeing is these core electrons right here are shielding the valence electron, who's trying to be bad. They're shielding that from the full power of the nucleus, from the power of the parents. So what this electron on the outside feels is a +1. So the Z effective equals a +1, which means the valence electron feels a +1 charge. So that means it's able to stray a little bit further from home, a little bit further from that nucleus. So any questions on anything here? All right, so let's continue on and let's do beryllium next. So we're doing Z effective. And we know it is number of protons minus our core electrons. All right, so taking a look at this beryllium right here. How many protons does beryllium have? All right, so I'm seeing 4. Any questions on how we figured out that beryllium has 4 protons? All right, so next we need our screening constant, which is going to be our core electrons. Oops. So you can use either method we talked about, but how many core electrons does beryllium have? All right, excellent. So I'm seeing 2 right here. So which method did you guys prefer? Did you prefer looking at the noble gas core, or did you prefer using the 4 minus the 2? All right, so we got 1 vote for the noble gas core, and then a couple votes for the 4 minus 2. Okay, but everybody has a method that they like that's going to work for them, yes? Okay. All right, so if our Z is 4 and our S is 2, what is Z effective? Excellent, 2. And I'm just going to put that plus 2 for emphasis. You don't have to write the plus. Any number, if you don't put a negative, I assume it to be a positive. All right. Any questions about how we found the effective nuclear charge for beryllium? So I know this is a really tough topic to kind of wrap your head around. So if you're stressed out about it, you're in good company. Just feel free to ask questions. Also remember at the end of class, after we get done with the lecture, we don't have lab today, but I'm here till 9:45. So if you want to talk about Z effective or anything else, I'm always here to talk. Questions on anything so far though? Okay, so it's just a little past 5:50, so I'm going to think of it as 5:50 and go ahead and take your break and go ahead and come back at 6 o'clock. All right, so let's go ahead and get started again. Oops. All right, any questions about what we were doing before before the break? All right, so we took a look at lithium and we found out lithium was a +1. We took a look at beryllium and beryllium was a +2. Let's go ahead and do one more here and then I'm going to show you another method. But first, let's try our boron. So we're going to be calculating Z effective, which will be our number of protons minus our core electrons. Oops. Sorry, it takes a minute to adjust the pages. All right, so we are doing boron right here. So how many protons?
Professor, we can't hear you.
Oh, I'm so sorry. Let's see. Let me go. Where did I go? Let's see. I'm so sorry about that. I forgot I had put myself on mute during break. Okay. Thank you for letting me know. All right. So let's start back and say any questions about what we did before break? Okay. So before break, we took a look at how to find the effective nuclear charge. And we took a look at lithium first, which was a +1. Beryllium, which is a +2. Now we're going to take a look at boron. And after boron, I'm going to show you another method. If you like this method, that's awesome. But I think the new method you'll like even better. But before we do that, let's go ahead and take one more look at the method we've been doing. And so this one is for boron. And there we go. All right, so here is boron right here. So how many protons in boron? All right, excellent. So I'm seeing lots of 5s. I feel so embarrassed. I was at a meeting the other day and we kept trying to wave down the person who was talking. We're like, we can't hear you. Anyways, so now I feel embarrassed because I did it too. Okay, so those are our protons. How about our core electrons for boron? How many core electrons? All right, so I'm hearing Andrew say 2. What do you all think? All right, excellent. So I'm seeing 2s and I'm seeing 3s. Okay, so we got 2s and 3s coming up. So let's talk about that. So first, let's use the method of the noble gas. So if I go up and I go to the right, how many electrons does helium have? 2. So based on our noble gas configuration, we should have 2 core electrons, but let's take a look at the other method. So the other method that we looked at the total electrons, and the total electrons are 5. Valence electrons right above here are 3. So the other method was 5 minus 3 equals 2. So I saw a few of you talking about 3 in there. Any questions why it's 2, not 3? So for me, the easiest way to find the core electrons, no matter which element I'm looking at, so here's germanium, is just to go up and to the right, and boom, it's 18. For lead, again, up and to the right, it's 54 like so. So that's the easiest method for me, but for those of you who prefer the subtraction, then what you're doing is taking the 5 minus the 3, like so. So for germanium, it would be something similar. But any questions? Okay. All right, so we're doing boron, and we know that we have 5 protons, and we said we had 2 of our core electrons. All right, so what is our effective nuclear charge? Okay, so here's where our 3 comes in. Excellent, so it is a 3, and again, I like to write that plus just to emphasize, but a regular 3 is just fine with me. All right, so any questions on how we got that effective nuclear charge for lithium, beryllium, and boron? All right, so now let's take a look at another method. So again, if you feel like you're comfortable with the method we're using, you don't have to do this. But I think most of you are going to like this. So first I'm going to take a look at the lithium. And so what we've been saying is that it is the total electrons, or the total electrons or the total protons minus the core. And so what our Z effective ends up being, now I should put an approximate here because this is just an approximation, is the valence electrons. So if you take the protons and you subtract out the core electrons, you are effectively using the valence electrons. So for lithium, it will be a +1. For beryllium, it will be a +2. For boron, it will be a +3. And so on. If we do carbon, it's going to be a +4. Nitrogen, it's going to be a +5. And I know some of you are like, hey, why did you waste my time with all that other stuff if all you had to say is the effective nuclear charge is the same as the valence electrons? I did it because I want to show you where it comes from, and I want you to really understand where the effective nuclear charge, or what it is. And I know you're thinking to yourself, no, you just like to torture us. Okay, maybe a little bit. No, I'm kidding. I'm doing that. I did it the long way first so that you could understand where it comes from. And for those of you who do choose to go on in chemistry and you do the full calculation, you're not like, she lied to me. Anyways, so let's keep going with our oxygen. It'll be 6. Fluorine, 7. And let's see if I could squeeze in one more. Finally, neon will be +8. Remember, if you were dealing with helium, helium is not +8. Helium is a +2 because it actually has 2 valence electrons. All right. So I find this to be, of all the methods that we looked at, the easiest. But any questions on how we did this method right here? Okay, so you're welcome to use this method that the effective nuclear charge is the same as the number of valence electrons. But I do still want you to understand what's going on with the effective nuclear charge, and that's why I made you suffer through all of this talk. All right, so questions on anything here? All right, so let's go ahead and take a look at all of these. And just rewrite them. All right, so what we see going from left to right is that the nucleus is getting stronger. The effective nucleus is getting stronger. So again, if you go back to our analogy, the power of the protons, the power of the parents, by the time you get to neon, you have some pretty strict parents. They aren't saying, hey, 6 p.m., you are going to bed, I want you asleep, you're going to get up early, you're going to clean the house before school, you're going to do all these things. So this is a case where you have a very small atom. Those electrons are being very tightly controlled. When you're over at lithium, I like to think of this as the laissez-faire parenting style. This is kind of the hippie parents that are like, oh, did you want to go to school tomorrow? You can go if you want. So here you have those electrons traveling quite a ways from the nucleus. And what we see going from left to right is they just gradually get smaller and smaller as those parents start finding their power and controlling their electrons a little better. So I'm going to attempt to do a little series here. So I am attempting to make them smaller and smaller. And now we've got to make my neon even smaller. All right, so this is my attempt at a little artistic series here. So all of them have a nucleus in the center there somewhere. And as we go from left to right, again, they're getting smaller and smaller because the nuclei is effectively getting stronger and stronger. Those parents are reading parenting books. They're being told you don't ask your kids if they want to go to school. You tell them they're going to school. And so by the time we get to neon, those electrons are under control. All right, but any questions on anything here about this series from left to right? We go from large to small. So I do want you to understand the theory of this. So be aware on a test or quiz, I could ask you to explain why do atoms get smaller as we move to the right of the periodic table. I could also ask you, why do they get smaller going up, or why do they get larger going down the periodic table? So I do want you to understand that theory. So if you have any questions on it, of course, feel free to let me know. All right, so any questions about anything we've talked about so far? All right, so next up we're going to talk about ionic size. So ionic size, these are when you have cations or anions. And first question says, what happens to the size of an element when you add electrons? So these are all the same element, so they all have the same Z effective. They all have the same effective nuclear charge, which means their parents or their nucleus are all equivalently strong. So I'm going to draw my sulfur right here. And then what we're going to see is as you add electrons, these ions are going to start getting bigger. So the idea is for the same effective nuclear charge, there's now more electrons to control. So let's say you are a parent and you got 4 kids, you got them pretty well under control, but now your sister or brother brought over some more kids, so now you've got 2 or 3 extra kids in the house for the weekend. It's a little harder to control them. So what we say is the power of those protons is now spread out across more electrons. So each individual electron is going to feel a little less of that power, and because they feel less power, they start drifting away a little bit. So here is it written out. So when we add electrons to form an anion, remember your anions are your negative ions. We will always increase the size. And the larger the negative charge, the larger the size. So a 2 minus will be larger than a 1 minus. So the positive charge of the nucleus is the same. That is your Z effective. However, it's now spread across more electrons, so each electron individually will feel less of that charge. So when I was younger, I was a camp counselor, and I've also been a high school teacher, and I know if you've got more rambunctious kids in the room, it is that much harder to control them. So I think of it as the power of the protons, the power of those parents in the center, now trying to control more 15-year-olds who don't want to be in, no, of course they want to be in chemistry class, 15-year-olds who maybe don't want to be in biology class. So as that power is spread out among more electrons, each individual electron, again, feels less of that power, and it starts drifting further from the nucleus. So any questions on what's going on here for our negative ions or anions, that the greater the negative charge there is, the more electrons there are, and the more it's going to spread further from the nucleus? All right, so next up we're going to talk about cations. So it says what happens to the size of an element when you remove electrons. So again, these are our cations. And here what we're going to see is it's going to get smaller. So here I'll start with calcium being big, calcium 1 plus being a little smaller, and calcium 2 plus being even smaller than that. And I'm just trying to draw relative here. I'm not using actual sizes. So what's going on is actually two things for our cations. The most important thing is that when we remove the electrons from a cation, we often are removing a shell. So for instance, sodium has an electron in the 3s shell, that's a third energy level. However, when we form a sodium ion, we're removing the third energy level, and now this is the 2s. So you have essentially removed a shell, taken off a jacket, and that's the primary thing that we see in terms of why our cations are smaller. But there is another reason, and this relates to what we saw for our anions. So the positive charge of the nucleus is now spread across fewer electrons. Thus, those elements feel a stronger attraction to the nucleus. So if you can remember our neon, which the parents very tightly controlled all of those electrons, but let's just imagine, I know neon doesn't normally lose electrons, but let's imagine it's decided a couple of its electrons can go spend the night somewhere. They went somewhere very healthy, very good. Maybe it's a math camp or a church camp, somewhere very healthy. And so now neon's protons can focus in on those other electrons, and it can even more tightly control them and make sure they are absolutely in bed by 6 p.m. So as we get to a positively charged ion, the protons can have more control over those valence electrons because there's fewer of them. So any questions on anything here? And I hope you don't mind my parenting analogies here. I actually don't have kids, but I do think of my 2 cats as my children. All right. So here is a size chart, and what I want to do first is just take a look at the cations here. All right, so here what we see in gray, these ones right here in the gray, that is the original element. So the cations are in red, and you see the cations are smaller. So as we had a positive charge, the electrons are going to sit closer to the nucleus. And here again you have beryllium, and the positive charge in red shows that this ion is smaller. So the cations, positive ions, are always smaller than the original element that's shown here in gray. So any questions on anything so far? All right, so let's head over here to the anions. You're going to notice here it's just shows some of the elements, just kind of truncates everything. But this does go over the entire periodic table, this trend. So here in the gray, these are our original elements. And now in the blue are our anions, our negative ions. So negative ions are always larger than the original atom was. So there's no exceptions to that. The anions which have gained electrons will always be larger. The cations which have lost electrons will always be smaller than their original atom. So any questions on anything here? All right, so next up we're going to move to ionization energy. So ionization energy is about how something forms a cation. So what we know is that sodium can form Na+, and what we haven't talked about yet is the amount of energy it takes to turn a normal sodium, a sodium atom, into a sodium ion. So that is our ionization energy, and by definition, the atoms need to be in a gaseous state. So it is the amount of energy needed to remove an electron, or I like to think of it as stealing an electron from sodium atom to turn it into sodium ion. Now in the real world, especially in the lab, you know that we don't always deal with gases. In fact, we rarely deal with gases. But this is a theoretical approach to looking at it. So we define ionization energy in terms of the gases, even though that's not the way it always happens, or even not the way it frequently happens in the real world. So we're going to talk more about this ionization energy, but any questions so far about this idea that you must put in an amount of energy to take an electron away from an atom, even if it's an atom that we know it's favorable for it to lose that electron. Sodium goes to bed dreaming about losing that electron. We still have to put in energy because we are still taking something away from sodium. So any questions on that? All right. So often we can remove more than one electron. That's how we get our 2+ and our 3+ and so on. So the first ionization energy, which we're going to call I1, I know it kind of looks like a 1 there, but that's really an I there. And this little guy is an I. So I1 is the energy needed to remove the first electron from the neutral atom. So any questions here? Good question. So Clinton, no, it is not the same energy when it's in a liquid or a solid state. So we've defined ionization energy as the gas. If you had it in a solid or in a liquid state, what we would do is we would calculate first how much energy is needed to, say, from a liquid vaporize into a gas, and then we'd use our ionization energy. Then we'd use how much energy it takes to condense it back down into a liquid, which is kind of a long thing, and we will actually do a similar calculation to that. And so the reason is that these are the published values in ionization energy. So if you have a liquid or solid, you have to essentially use Hess's law to convert it into a gas before you can use this value. I know it would be easier if we published them in liquid or solid state. I'm not entirely sure why we publish them only in gas state. I can look into that and find out, but yeah, I know it makes everybody's life a little tougher, but we get to do these really cool lattice energy problems because of it. So. All right. Any questions on anything here? All right. So next up, it is harder to remove an electron from a small atom because it holds its electrons more tightly. Thus, it requires more ionization energy. And conversely, it's easier to remove electron from a large atom that's holding its electrons more loosely. Thus, it requires less ionization energy. So thus far, I've been telling you about the power of the protons, the power of the parents at the center of this atom. So if you're talking about something small like fluorine, it is tiny because it's holding on to those electrons. It's got a really tight grip on them. So if you have a small atom, any small atom, it's going to be tough to take an electron away because it's hanging on tightly. That's what makes it small. So you'll have to put in a lot of energy to take an electron away. On the other hand, if you have a large atom like real big, RB, it does not have a very strong nucleus. So the protons, the parents in the center, those are the hippie parents that are like, yeah, be back by 2 a.m., everybody. So the electrons are drifting further apart, so it's easier for us to take an electron from that really large atom. So I want to tell you a story, and again, feel free to cover your ears if you are not happy about this, about my analogies. And we're going to talk about fluorine, and we're going to talk about real big over here, which the official name is rubidium. And this is a little easier to do when we're in class. But let me talk about fluorine first. So fluorine is strolling down the street, and this is before social distancing. So strolling down the street, it has its brand new iPhone in its hand. I don't have an iPhone, I have a cheap generic phone. But fluorine is not like me. Fluorine is a very cool little atom, and it's got a brand new iPhone. And so it's got its iPhone, and it's strolling down the street downtown, 2 in the morning, cruising along. But fluorine keeps close track of its electrons. That's why it's so small. So it's not just really strolling like so. It is hanging on to that electron, hanging on to that iPhone. And as it goes down the street, it's checking, looking everywhere. Is there anyone trying to steal my electron? And let's say you are like, hey, I need that phone more than fluorine does. I'm going to take that electron or that phone from fluorine. You can do it. But fluorine is going to fight back, and it's going to fight back with everything it has. And it might just take off a piece of your ear. So yes, it's possible to take an electron away from something like fluorine, but because they're so small, and because they are so powerful, they are small but mighty, they will fight back, and you will have a huge ionization energy. On the other hand, real big, strolling downtown, middle of the night, and someone's like, hey, I need that phone. And real big is like, okay, sure, I wasn't using it anyways. So real big is not keeping strong control over its electrons. It is just letting them fly around quite a bit. So for another atom to come up and steal an electron doesn't cost very much energy. But for any of our small elements like fluorine, they have an iron grip on those electrons. That's how they got to be so small. So if you want to steal from fluorine, and it is possible, you've got to put in enough energy and be prepared to lose a piece of your ear, but you can take something away from fluorine. And on that note, and I'm sure it's much safer nowadays than back when I was a student, but back when I was a student, they used to joke about fluorine chemists. And they would say, yeah, you can always tell a fluorine chemist because they're usually missing at least one finger, because fluorine can be so volatile when you are trying to take away an electron that explosions would often happen. And fluorine chemists, they kind of knew that going in, that they're essentially working with explosives. And it was very common at that time to have a fluorine chemist that was missing a finger from those experiments. I'm sure it's safer now. Those of you who love fluorine and want to go into fluorine chemistry, I'm sure it's safer nowadays. But any questions on that idea that the smaller the atom, the greater the ionization energy, because they're hanging on to those electrons much more tightly, and the larger the atom is, the more loosely it's hanging on to those electrons, so you won't have to put very much energy to steal an electron from them? This is kind of weird because normally when I tell my stories, I can see your faces, so I can see if you guys are enjoying the story or if you got like your head in your hands like, oh my god, this is the lamest story ever. So it's kind of hard to do this without seeing all of you. Okay, well, at least I hope the story wasn't terrible for you. So any questions on this idea that it's harder to remove an electron from a small atom because it holds its electrons tightly, and therefore it will require more energy, and that IE is the ionization energy, and that it's easier to remove an electron from a large atom, and therefore that would require less ionization energy? Awesome, thank you. Excellent. do actually have a story about a fluorine chemist, but maybe I'll save it to the end of class if you guys have any energy left for another story. Okay, so next up, ionization energy versus atomic number. So if we go back to our chart, we know that ionization energy is going to increase going up and increase, going to the right. So again, what we're doing is we're following the trend of the sizes. So smaller it is, the greater the ionization energy. The larger it is, the less the ionization energy. But be aware, everything has an ionization energy. You cannot steal an electron, even from somebody who wants to give it to you, without putting in a little bit of energy. All right, so now on this chart, what we're doing is we're going across the periodic table, across the period. So when I go here up, what I'm really doing is going across. So we have essentially, and I don't know if I can do this on the iPad, taken the periodic table,